All right, so now that we have understanding of pressure and a little bit of background information, this video is going to go through the various gas laws we have. We'll be looking at some demos of it and practicing math problems with it as well. So to get started, let's do a little bit of review. So what does it mean when we say STP? It means that STP means standard temperature and pressure. Yeah, I'm writing that really poorly. All right. And what temperature unit do we need to use with gas laws? We brought this up in the last PowerPoint. We use Kelvin. And lastly, what is molar volume? It's that at standard temperature and pressure, at STP, 1 mole of any gas occupies 22.4 liters of space. All right. So just a little review because we'll be using all these concepts throughout this video. All right, so we're first going to take a look here at a somewhat of a demo to get an idea of our first gas law.
Mr. K. Today I want to show you how to inflate a balloon without blowing.
So what we need here is a plastic bottle, vinegar, a baking soda, a funnel, a balloon, and a rubber band.
Now I am going to pour the baking soda in the balloon. So now I'm going to pour the vinegar into the bottle.
So next I'm going to put the balloon over the bottles, but without tipping all the baking powder inside the vinegar. So once we secure it with the rubber band, we can tip the balloon over now with the baking soda and see what happened. Do you want to move away? Do you want to move away? Can you see the balloon?
Yep. It's growing.
Yeah. It's growing bigger and bigger.
It looks like it's going to blow.
It's going to burst? No.
When the baking powder and the vinegar are mixed together, it will release CO2 and inflate the balloon. Bye-bye.
All right. So as he told us in the end there, right, that reaction was generating gas. So as we added more gas to the balloon, what happened to it? Well, obviously, right, we saw it grow, we saw it increase in size. And so this takes us to our first gas law, which is Avogadro's law. So Avogadro's law tells us the volume of a gas at constant pressure and temperature varies directly with the number of moles. Mathematically, what this means is our volume is going to equal some constant K times our number of moles. So, just so we can start writing notes here, a big V there stands for volume. N stands for number of moles. And K is some constant. And so what we can then do to this is we can manipulate it in order to solve for how it's going to change. Because that's what we look at with a lot of these gas laws, is if we have one set of conditions and we change one of them, how is the other changing? So what we can also say with this is our initial volume divided by our initial number of moles is going to equal our new volume divided by a new number of moles. So V1 over N1 equals V2 over N2. So let's try out a problem with this. A balloon's volume is doubled. If it initially had 3.4 moles of a gas in it, how many does it have now? So we're going to follow the same general guidelines that we always do with word problems. We're going to underline the things we know and circle what we're looking for, or try to identify what we're looking for. So we're told the volume is doubled, and it initially has 3.4 moles of gas. And it's asking how many does it have now, and so that means, right, like, so that how many, we're looking at moles. So if we list all of the stuff we know, so our N1 is 3.4 moles, and we're looking for N2. And so now with identifying our volume, so our V1 and V2, right, we're told that it doubled. And so we don't have any actual values for this, but double just means like 2 times what it changed to, right? So we could pick any values, but the easiest values to pick are 1 and 2, right? That's clearly a doubling in volume if we have 1 and 2. So I'm just going to shrink this up here so I have some more space. So now we're going to be using V1 over N1 equals V2 over N2, and we want to solve for N2. So we're going to cross multiply, so V1 times N2 equals V2 times N1. We're looking for N2, so now we're going to divide both sides by V1. And so we're going to have N2 equals V2 N1 over V1. And we plug in our values. So V2 is 2. We're going to multiply that by 3.4 moles. Divide by 1. And so we get N2 is equal to 6.8 moles. All right. So let's have you try this problem now. What you should have gotten was 36 liters. If you didn't get this, I think a big thing here to notice is that it says 5 more moles of gas were added. So be sure that your N2 is 4 plus 5, not just 5. All right, so let's take a look at another demonstration here.
We filled this barrel with a couple inches of water, and we heated it up so, as you can see, it's like turning into steam. And then we're gonna quickly put this can filled with steam into the bucket of ice water, and it should crush. That's because it's going to go through a rapid phase change where the steam is going to condense quickly into water vapor, and pressure inside of the can is going to be less than the pressure from the outside, and it should crush. It should implode.
Tight. Twist. Twist.
That's hot. You don't want to hear it? I don't want to hear it.
That's fine. Squeeze.
Should I sign something?
Sure is.
I want a single. Come on, go!
Oh no, just grab the ice, you, and then with your hands. That is so wimpy.
Well, I'm scared that it's gonna blow up in my face.
Wait, no.
Mr. Abrams, do it. Yeah.
It's gonna be great.
Okay, so she kind of explained it in there, but why did that can implode when it finally got cold enough? And as she said, right, it was because initially that can was really hot, and so this steam in it was occupying a lot of space, maybe even left the barrel itself. And then as it got cold, all the steam and hot air condensed, and so there was less pressure inside of the barrel than there was on the outside, and so the can collapsed. So what does that tell us then about the relationship between temperature and pressure? Well, what it tells us is that they are directly proportional, because as we saw the temperature go down, we saw the pressure in the can go down as well. So part of this is because as we heat a gas, it's going to expand a lot. Because of that, remember with the kinetic molecular theory, if we heat something up, if we heat that gas up, it's going to move around more and collide more. And so those increase in collisions are going to cause it to expand and take up more space. This is why, we need to be careful whenever we have a container with a lot of pressure in it, that we don't heat it up, because it can be very dangerous. If you've ever used a pressure cooker, they lock on the lid and have a vent, so that way when you're ready to actually open it up, you can open up that vent, let all that hot air out, and not have an explosion in your face if you just try to open it. So as we said, temperature and pressure are directly proportional. And what this means is, for gas, a higher temperature means more pressure, or higher pressure. And vice versa. So if we have a lower temperature, we're going to have less pressure. And this is due to, as we heat a gas, the gas particles are moving faster and colliding with the walls with more force. Right? And this is exactly why you should never throw an aerosol can into a fire, because it's going to, they're already super pressurized, and so if you throw that in, it's going to cause a really big explosion. So please don't do that. All right. And so the law that tells us about this is Gay-Lussac's law. And so he says that a pressure of a fixed mass of a gas at constant volume varies directly with the temperature in Kelvin. So mathematically, that means we're looking at pressure equals some constant K times temperature. This is a different K than what we listed earlier. We just use K as a general constant. So again, P means pressure, and T means temperature. And remember that we have to use Kelvin for temperature. And so just like how we used Avogadro's law to look at one set of conditions and how the others will change, we do that with this law as well. So our initial pressure over our initial temperature is equal to a new pressure over a new temperature. So let's give this a shot. So at 120 degrees Celsius, the pressure of a sample of nitrogen is 1.07 atmospheres. What will the pressure be at pressure be at 205 degrees Celsius, assuming constant volume. So we're told we're at 120 degrees Celsius, and the pressure is 1.07 atmospheres. And we want to know what the new pressure is at 205 degrees Celsius. So we have a P1 of 1.07 atmospheres, and we're looking for our new pressure. Our initial temperature is 120 degrees Celsius. Remember, though, we have to convert this to Kelvin. So we're going to add 273, and we get 393 Kelvin. And then our new temperature, T2, was 205 degrees Celsius. Again, we have to convert that into Kelvin. So we're going to add 273 to it, and we get 478 Kelvin. So the equation that we're using, so we have P1 over T1 equals P2 over T2. We're looking for P2, so we're going to multiply T2 to the other side. So we're going to get P2 is equal to P1 times T2 over T1. We're going to plug in our values. So 1.07 atmospheres times 478 Kelvin divided by 393 Kelvin, and you should get the new pressure to be 1.30 atmospheres. All right, so let's have you give this a try now. All right, so for this, you should have gotten that it was 335 degrees Celsius. Remember that you need to convert this degrees Celsius to Kelvin, and you're solving for Kelvin. Temperature's the only measurement that we use here that has to be in a certain unit. Because both of these are millimeters of mercury, you don't need to convert your pressure at all, because the units are going to cancel just fine there, and you'd create more of a ratio. Also be sure that you need to that you're solving for T2, and so hopefully how you plugged it in was T2 equals T1 P2 over P1. So if you didn't convert it that way, that could be part of the problem if you didn't get the correct answer there. All right. Okay, so let's take a look at a third demo here.
Marshmallow. And a peep. On a clean plate. Put in a Del jar. Hooked up to a vacuum pump. Flip it on. They've expanded as much as they will. Here's the fun part though. Turn it off. Close the valve. Disconnect. Here we go. there's our peep and marshmallow afterwards. Good stuff.
All right, so that vacuum pump was removing the air from that bell jar apparatus. So why was the peep expanding? Well, the peep was expanding because now there's no longer particles of air putting pressure on it, and so it was able to grow in size because now it's not having as much air pressure being pushed down on it. It shrunk down because of the air pressure, because when the air particles were allowed back in, that pressure returned, and so it collapsed. So this tells us that volume and pressure are inversely proportional. Right? If we take a container of gas, so like think of a balloon, and squish it down, we're making the volume smaller. But the pressure in the container is going to get larger. This is because now the particles are hitting the walls of the container more often. Right, this is why if we take a balloon and we sit on it, we're squeezing the balloon into a smaller volume. And so the pressure is going to increase so much that it will break the balloon. Looking at another way, we have, if we look at a container with a piston, right? So if this is 1 liter and we have a certain amount of air in it, right? They have more space. They have more area to collide with the walls, and they have more space themselves. But if we were to half that container in size, well, now there's less area for it to collide with, and the air is more densely packed, so the particles are going to be hitting way more often. And so that's what's going to lead to that greater pressure. See if I can do that way. So this is Boyle's law, and this tells us that the volume of a fixed mass of gas varies inversely with the pressure at constant temperature. And so let's watch a video on that.
The next thing we're going to learn about is the gas laws. There are 3 of them, and the first one is called Boyle's Law. Now, we are the gas particles, and we're inside a box. Just a regular box, but we're a very, very special gas. We're called an ideal gas. Whee! Listen, boys, we're an ideal gas. Way! But what does that mean? Well, because we're an ideal gas, that means we have to follow special rules. The first rule of Ideal Gas Club is there are lots and lots and lots of particles. The second rule of Gas Club is that when we're bouncing off each other, these collisions are perfectly elastic. Can you remember what that means? It means that there's no energy lost in the collision. The third rule of Gas Club is that when we're bouncing around, the only time we interact with each other is when we hit off each other. There are no forces between us. And the last thing about us, the last law of Gas Club, is that we're very, very small. That means that the box is mostly filled with space. So that's the rules for being in an ideal gas. Whee! Now, the first gas law we're going to learn about is Boyle's Law, or as the French would call it, Le Mariotte Law, or something like that. Boyle's Law concerns the gas particles in a box, and I want you to think about us bouncing off the walls and bouncing off each other, but we're going to change something, okay? We're going to change the volume of the container. The temperature is not going to change. That's absolutely certain. The temperature is not going to change. We're going to keep it the same. But we're going to change the volume. Now, you can see it's bouncing around. What do you think will happen if the volume of this container is cut in half? Have a guess. collisions doubled, you'd be right. That's what happens. Look, regular size container, we're bouncing off like this. B, ooh, E, ah. But when you cut the container in two, look, ooh, E, ooh, E, ooh. It's such a laugh. So as you can see, the pressure and the volume are inversely proportional to each other. When you double one, the other one halves.
All right. So yeah, so as they showed in that video, pressure and volume are inversely proportional. What this means then, if we multiply them together, so pressure times volume, that's going to equal some constant K. Again, that K can be anything. How we actually apply this is P1 times V1, so initial pressure times the initial volume, is going to equal P2 times V2. So let's apply this. So if you have 1 liter of a gas and it has a pressure of 1 atmosphere, if the volume expands to 5 liters, what is the new pressure? So we have 1 liter, a pressure of 1 atmospheres, the volume expands to 5 liters, and we're looking for the new pressure. So V1 is 1 liter, V2 is 5 liters, P1 is 1 atmosphere, and we're looking for P2. So we're using P1 times V1 equals P2 times V2. We're looking for P2, so we're going to divide both sides by V2. So we have P2 is equal to P1 V1 over V2. So we plug in our values. So 1 atmosphere times 1 liter divided by 5 liters. So we're going to do basically 1 divided by 5, and you should get 0.20 atmospheres. All right. So let's have you give this a try. All right, so what you should have gotten for your answer is 28 liters. Remember, if you see something like it being double, one value being doubled, that just means that you can use its initial as 1 and its final as 2. It's just that simple there. So what you would have done was like 56 divided by 2 to get that. All right, so let's watch one more video, I think.
As children.
Sorry, if I pause it, it stops that whole thing. Guess you could have paused there and read that. So why did the water rise up when the candle went out? All right, so as the gas in the glass, that became hot and escaped. And so then once we put the cup over it, the temperature, and the candle went out, the temperature decreased, causing the gas in it to condense and take up less space. And so the volume, we can't just like lose that space. So the water rose up to accommodate that dropping in volume there. by the gas. So this tells us then that temperature and volume are directly proportional. And so what that means is as we heat a gas that's not in a fixed container, the gas will expand. And if we cool it, it's going to contract. So what this is actually why hot air rises and how we can use like hot air balloons. Because as the air expands, if we're in a container, that means then that container now has air that's less dense than the air around it. And as we know, if something's less dense, it rises up because now it's going to be lighter and take up less space. And so that's why we can like use hot air balloons to go up in the air. And this is Charles' law. So Charles' law is that the volume of a fixed mass of a gas at constant pressure varies directly with the Kelvin temperature. So we're going to watch another video here on that.
The second gas law we're going to look at is Charles's law. And Charles's law is what happens when about the volume and the temperature. And in this case, we're got to keep the pressure the same. Okay? Got to keep the pressure the same. Now, what we're going to do is, as you can see, there's some flames under this box. Ooh! Which means the temperature's going to rise. But if we've got to keep the pressure the same, what's got to happen to the volume? Well, let's see what happens when we keep the volume the same and the temperature goes up. Ooh, ee, ah, ee, ooh, ee, ooh, ee, stop, 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 stop. Well, what happened there was, when the temperature went up and the volume stayed the same, we bounced off the walls and we bounced off each other, which means the pressure went up, and that's no good. So what have we got to do to keep the pressure the same when these funny little flames tickle us from below? Have a guess. Well, the challenge was to try and keep the pressure the same while these flames tickle us from below. Now, if you've guessed that we need to increase the volume of this container, you were right. Look, let's start off in this normal sized container. Watch it as bouncing off the walls. Ooh, ee, ooh, ee, ooh, ee, ooh. Now, the Bunsen comes on underneath, but let's double the size of the container. Ooh, ee, ooh, ee, ooh. Ah, that did it. We kept the pressure the same. That was a demonstration of Charles' law, that volume being directly proportional to the temperature when we keep the pressure the same. See if you can remember that one.
All right. So Charles' law, the volume of a gas is directly proportional with the Kelvin temperature. So the way that we write that, so volume is equal to some constant times temperature. And the way that we apply it is our initial volume over our initial temperature equals our new volume over our new temperature. So let's give this a try. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. What volume will the gas occupy at 50 degrees Celsius if the pressure is constant? So we have a volume of 752 milliliters at 25 degrees Celsius. We want to know what the new volume is going to be at 50 degrees Celsius. So V1 is 752 milliliters, and we're looking for V2. T1 is 25 degrees Celsius, and remember we need to use Kelvin temperature, so we're going to add 273 to it, and we get 298 Kelvin. T2 is 50 degrees Celsius. Again, we have to convert that to Kelvin, so that's 273, so that's 323 Kelvin. So notice that in terms of Celsius, it looks like we doubled the temperature, but in Kelvin we didn't really double the temperature. So I don't usually do like doubling with temperatures because of that issue. I just want you to be aware, if it looks doubled in Celsius, that doesn't necessarily mean that it was truly doubled. Okay, so we're using V1 over T1 equals V2 over T2. We're looking for V2, so we're going to multiply T2 to both sides. So we get V2 is equal to T2 times V1 over T1. So we plug in our values. So 323 Kelvin times 752 milliliters over 298 Kelvin. And you should get 815 milliliters. Now notice, just like how when we're dealing with pressure, it doesn't really matter what unit we're using at this point. It's only when it comes to temperature that we have to worry about it. With our volume, we can leave it in milliliters because we can answer it in milliliters. Now, if I had asked you to solve it for liters, so if I said, what will the volume be in liters, then that's when you would want to convert it, but at this point, it's not necessary. So let's have you give a shot here. So answer this question. Okay, so for this one, you should have found that the new temperature was 888 Kelvin, or if you converted that back to Celsius, 615 degrees Celsius. I didn't ask you specifically for Celsius in this one, so if you didn't convert it to Celsius, that's totally fine. I just wanted to give you both in case you did. But remember that this here does need to be converted to Kelvin no matter what. Again, when we see something like tripled, that means that we could say that V1 was 1 and V2 then is 3. Also be sure that you solved it correctly. So if it's usually V1 over T1 equals V2 over T2, the first thing you'd want to do is cross multiply. So V1 times T2 equals T1 times V2. And then we would divide both sides by V1. So T2 equals T1 times V2 over V1. All right. So we have one last law here, and it's called the combined gas law. So this is where we take in all of these factors that we've been discussing and turn it into one formula. And so the combined gas law is P1 times V1 over T1 equals P2 V2 over T2. This is the equation that you get on your cheat sheet because if one of the variables doesn't change, you can just kind of eliminate it, right? If we're not looking, if you're told that the pressure changes and what's the new volume and the temperature's constant, you would just eliminate out temperature here. So you can, that's why we just give you this equation on the test, because you should be able to manipulate it no matter which way you decide to, what you need to use it for. I was going to say, remember as well that we always use Kelvin as our temperature unit here. So let's give a problem a try. So we have a volume of a gas is 27.5 milliliters at 22 degrees Celsius and 0.947 or 0.974 atmospheres. What will the volume be at 15 degrees Celsius and 0.993 atmospheres? So are we told we have a volume, or V1, is 27.5 milliliters. Our T1 is 22 degrees Celsius. Now remember, we need that in Kelvin, so we're going to add 273 to it. So that is 295 Kelvin. And our P1 is 0.974 atmospheres. We're looking for our new volume. Our T2 is 15 degrees Celsius. Again, we need to convert that to Kelvin, so we're going to add 273 to it, and we get 288 Kelvin for that. And our P2 is 0.993 atmospheres. So we're using P1 V1 over T1 equals P2 V2 over T2. We're looking for V2, so we're going to multiply T2 to both sides and divide both sides by P2. So that way they cancel here and move over to the other side. So we get V2 is equal to T2 P1 V1 over P2 T1. So plugging in our values, we have 288 Kelvin times our first pressure, which was 0.974 atmospheres, and our initial volume of 27.5 milliliters. We're going to divide that by our new pressure, which is 0.993 atmospheres, and also divided by our initial temperature of 295 Kelvin. So you would solve this, and you should get that V2 is 26.3 milliliters. All right. So let's have you give this a try. The volume of a gas-filled balloon is 30 liters at 40 degrees Celsius and 1.15 atmospheres. What would be the volume of the gas at standard temperature and pressure? Okay, so for this one, you should have found that the new volume was 39.5 liters. Remember that we need to convert this 40 degrees Celsius to Kelvin. Also remember, standard temperature and pressure means our pressure, it's going to be P2, not P1. Our pressure is 1 atmosphere, and our temperature is 273 Kelvin. All right. So, one last law to cover here, and it's the ideal gas law. And this also combines in all of the laws we just talked about, but now instead of looking at changing conditions like we did with the when we're solving all these other problems, or with the combined gas law, the ideal gas law is looking at one set of conditions and one of the missing variables. So, right, we are going to combine Boyle's law, Charles' law, and Avogadro's law. And so if we do this, right, we see that volume is always on one side here. So we have volume, and that's going to be equal to, we have temperature and number of moles on top, and pressure on bottom here. Now remember, this proportionate symbol that we're given, so right now we just have like a proportionate, so we need some sort of constant. And so we actually use R as our constant here. We're going to rearrange this so it's all in one line. And so what we get is P times V equals nRT. And this is the ideal gas law. R is the gas constant. And it can have a lot of different values, and so we're going to actually calculate that value next here. And a way to remember it is pervnert. So it's just kind of one way to like remember the order, remember how it goes. And again, this is if we are looking at one set of conditions and are missing one of those variables, so we can solve for it. So why don't we try to figure out what that R value is. So we've solved the ideal gas law here for R. And so we're going to do this for 1 mole of gas at STP. So at STP, our pressure is 1 atmosphere. And if we have 1 mole of gas, that means that our volume is occupying 22.4 liters of space, because remember that is molar volume. N is 1 mole. And our temperature at STP is 273 Kelvin. So you do 22.4 divided by 273, and what you should get is 0.082, we're going to round it to 1, liters times atmospheres over mole times Kelvin. Now, when it comes to our gas constant, the value can change if the units change. So actually, if you look up gas constant on like Wikipedia, it has a huge table of all these different options for it. So here, we're only going to deal with 2. And so here we're looking at it in atmospheres, but we can convert that so that we're looking at it if we're using the pressure in kilopascals. So if you remember, 1 atmosphere is 101.3 kilopascals. So we can convert that to that. So we would do 0.0821 liters times atmosphere over mole times Kelvin. So I'm going to do kind of like this. So if we want to convert atmospheres to kilopascals, we're going to have 1 atmosphere on bottom, 101.3 kilopascals on top. So we can see atmospheres cancel. And so now our pressure unit's going to be in kilopascals. And we get 8.31. And our unit now is liters times kilopascals over mole times Kelvin. So both of these are our values. The difference is our unit of pressure. So you're going to try to choose which one to use based off of that. If you're not given a pressure and that's what you're looking for, you can choose either one if I don't tell you specifically which one to look for. So let's give this a shot. So we have a sample of argon in a 1.5 liter container with a pressure of 0.96 atmospheres. If the temperature is 15 degrees Celsius, how many moles are in the container? So we have a volume of 1.5 liters, and it has a pressure of 0.96 atmospheres. We want to know the temperature, we're not looking for the temperature. We want to know, our temperature is 15 degrees Celsius. Again, we need to do this in Kelvin, so we're going to add 273 to it. And so we get 288 Kelvin. And we're looking for moles. So N is our unknown. Because we have atmospheres, we're going to be using our R value of 0.0821 liters times atmosphere over mole times Kelvin. So and what you can see here, right, is we're not changing any conditions. So this is why we want to use the ideal gas law. So we're going to use PV PV equals nRT. And we're looking for N, so we're going to divide both sides by RT. So we get N equals PV over RT. So P is 0.96 atmospheres. V is 1.5 liters. We're going to divide that by R, 0.0821 liters times atmosphere over mole times Kelvin, and then multiply by our temperature in Kelvin, so 288 Kelvin. And we get 0.06 moles. Now, I want to take a look at this dimensional analysis here. So on top we have atmospheres, and we're multiplying by liters. Underneath, we know for sure we're dividing by Kelvin, and then if we look at the gas constant units, it's a fraction, and remember when you're dividing by a fraction, that's really like multiplying by the reciprocal. So we would put moles times Kelvin on top, and atmospheres times liters on bottom. So we can see our liter unit is canceling, our atmosphere unit is canceling, and our Kelvin is canceling, leaving us with moles. So dimensionally, it does work out correctly as well. So let's have you give it a shot here. So what volume would 0.7 moles of nitric oxide gas occupy at 3.12 atmospheres and 18 degrees Celsius? All right, so for this, you should have found that the volume was 5.36 liters. Some notes, if you didn't get it, remember you need to convert Celsius to Kelvin. Also be sure you're using the right R value for atmospheres. All right, so that is all of the gas laws. So there is a worksheet for practicing all of these again, so that way you can get some refinedness with it.